Hey, welcome back. This is section 3-2, Calculus 1. We are talking about derivatives as functions and some of their characteristics as well as applications. We are going to start with a theorem. We're going to say f of x is a function and a point A, is in the domain of f. So if f is differentiable at that point A, which means you can take the derivative or use the difference quotient, then f of x is also continuous at that point A. All right, so this is a tie between continuity and differentiability. So that means that if you can find the derivative, if you can find the slope of a tangent line at a point, then the function is also continuous at that point. Okay, well, a question arises, what makes a function differentiable? Okay, and it's easier to actually look at the problems than the functions that work. So let's ask this question. Where are there problems with differentiation? Which means where are we not able to find the slope of the tangent line? Well, the first this is not mathematical language, but the problems that we have are at points, pointy places, at vertical lines, and at breaks, and what I call jumpy functions. Okay, so let's draw pictures. Points. Anything with a pointy edge is going to create a problem. So the first things that come to mind with that are often absolute value functions. So here's an absolute value function. The problem is right here, because if I'm going to draw a tangent line, this right here is a tangent line. Okay, that goes through the one point. But this is also a tangent line. See, the problem with a point is that I can kind of spin that tangent line, if you will, in multiple directions and create multiple slopes on there. So it has to actually be a smooth curve in order to draw one unique tangent line. So that's the problem with points. Pointy places on the graph. So anything that comes, like if you've got a graph that comes up to a point, let me draw that better. If it comes like up to a point like this and then drops down, this is not going to be differentiable at this value right there, whatever that is. Okay, the rest of it is, but just that point is not differentiable. Vertical lines, functions that that go vertical for a second. So, for example, something that might come in like this and go vertical and then like that, because that tangent line is actually vertical and it has an undefined slope. So those are problems, and that's not differentiable right there. Obviously, breaks have the same problem as points, you know, because you're creating a point at the end of the break. I can, again, draw a tangent line, you know, many different ways through that point, and that's a problem. So all of these places, right here, right here, right here, are places on these graphs that are not differentiable. So what this theorem is saying is all the other places, because they're differentiable, means that it's continuous. Okay. Notice, I'm going to get to jumpy functions in a second, but just notice for real quick before we do that, The opposite's not true. If f is continuous, then f is differentiable. If we flip that around and go backwards, that's actually not true. Take, for example, this function right here. That is a continuous function. There are no breaks and no holes and no asymptotes, but it's not differentiable at that point. So this theorem only goes in one direction. Okay. Now, what are jumpy functions? These are kind of interesting. I've got a screenshot of this graph. This is the graph of x times sine of 1 over x. And here's what this does. If you see, it oscillates up, down, up, down, up, down. And those oscillations get smaller and smaller, but they continue on. If you zoom into this graph, it just continues on and on and on. So I'm going to look at it in this area where you can kind of see what's happening, but know that this happens all the way into the center. The problem is that your tangent lines, like here's a point. This tangent line is here, okay, and it's really steep, so, but it's roughly positive. But if I go over to the next cycle here and draw a point, then here's my tangent line, and that slope is actually negative. So the slopes of these tangent lines are constantly flip-flopping, positive, negative. And so that creates a situation where this is actually not differentiable as you get in here towards 0. So that is another problematic function with differentiability. All right. So there's a couple questions in your homework regarding that concept. Let's talk about some other things. Second derivatives. Second derivative is basically doing the derivative twice. Okay, so for example, let's just do a simple all right, if I want to find the first find the derivative, I'm going to take this, I'm going to plug it into my difference quotient. Okay, I'm going to multiply some stuff out. So this is from last section. Hopefully you did some homework, you're good with this. All my non-h terms cancel, and I'm going to factor in h out of the top. And that makes my h's cancel, and then I can plug in 0, actually take the limit, and I get 2x. So we'd say the first derivative is 2x. Now, I can ask you to find the second derivative. The notation for that is f double prime x, two derivatives. And what I'm going to do now is take my first derivative and do it again. So I'm going to take the limit as h goes to 0, but now I'm using this as my function. So I'm going to plug in x plus h, then I'm going to subtract the function, and then divide by h. So let's see what happens here. This becomes 2x plus 2h. And my non-h terms cancel. And in this case, I'm only left with one term on the top and the bottom. So I don't have to factor. I can just cancel the h. And I get a straight up 2. There's no h's left. It's just 2. And that is my answer. That's the second derivative. So that's how those work. You just do it twice. And why are we doing all this? What is the purpose and what do they do for us? There's tons of applications, but the one that we are going to use most, we'll do a little bit with some business and economics later, but for now we're going to go into physics land. The velocity of a function, of an object, is actually the first derivative. And the second derivative is the acceleration. And the function itself, the original function, is the position. So here's how these problems go. You'll say, like, I'm throwing a ball in the air and give you a function that models the path of the ball. If you take the derivative of that function, you'll get the velocity function. And if you take the derivative again, you'll get the acceleration. And then you can calculate the velocity or acceleration at any one point. It's pretty cool, and we'll do some more examples of those later. I'm just going to mention that now so that when you have a problem that says velocity, you should think, oh, that's the derivative, and acceleration is the second derivative. The last thing we want to look at is, what does the derivative look like if we draw it? So let's start by drawing a function. We'll make it a cubic. So somewhere, okay. So this is gonna look, oh, use your imagination. It's supposed to be a fantastic drawing. All right, so let's say we have this as our function. This is just a series of coordinates. Okay, if we want to, we could make an XY chart. It's a series of points. Let's say, for example, if x is -1, so here's -1, we could go up here and say the function is 5. Okay, at 0, we get up almost to 6. Let's say, I don't know, 5.5. These are estimates, by the way. At +1, maybe we're back down at 5. You get the idea. Let's jump out to 3. At 3, we're at 0. That point right there. At, let's say, 4, we're going to be down here at 1, 2, 3, 4, roughly -4, let's say. At about 5.5, we get to the bottom. So let's say 5.5 is 1, 2, 3, 4, 5, 6, 7, -7, and then we start going back up again. Let's jump over to 6, 7, let's say 8. At 8, we're down here at -4, and at 9, we're up at 0 again. Okay, that's a bunch of points. But that's, and it's not all the points, I just kind of picked a grouping of points. Let's see what happens to those points when we look at the derivative. We'll start with the chart. We are going to use the same x coordinates, and again, those were just chosen at random, but we'll choose the same ones. But when we're talking about the derivative, we're evaluating not the position, but the slope of the tangent line. So here's what this looks like. We're going to go to -1. This is our -1 place. That's not dark enough. Let me try a different color. Here we go. Ugh, struggle is real. Okay, -1. And we're going to go up to the graph, and instead of naming this y-coordinate, we're actually drawing a tangent line because we're going to graph the derivative, and we're asking ourselves, what is that slope? All right, now again, this is an estimate, so give yourself a little grace, but I don't know, it's roughly up 1/1, I'd say, maybe a little less than that, but let's call it 1. Okay. What happens at 0? At 0, right here, if I draw a tangent line, that's a horizontal line right there. That's flat. So this actually has a 0 slope at 0. Next point, 1. Here's 1. Let's go up and draw our tangent line. And now all of a sudden the slope is negative, and it's roughly a -1, let's say. But by the time we get to 3, right here, this tangent line minus my bump that I made in my drawing is actually, it's steeper. It's still in the negative direction, but it's steeper. Let's call it, it looks like maybe it's a -3. Okay, and we can continue along. 4, I think, is a little less steep in the negative direction. Maybe it's about -1. At 5.5, we get back to 0 because it's a horizontal line there. We jump over to 8, and we're at about, now we're a positive slope. Let's call that, I don't know, maybe 2. And by the time we get up to 9 again, we are fairly steep. Maybe it's a 4 or something like that. Okay, now let's plot these and see what they look like. So again, what I want you to pull from this is when you're asked to make a chart or graph of the derivative, you are graphing and charting the slopes of the tangent lines. Okay, so I'm going to just plot these points now. We're going to take a look at them. -1, 1, 0, 0, 1, -1, 3, -3, 4, -1, 5.5 is about 0, 6, 7, 8 is about 2, and 4. So if you'll see what it turns out, now we were estimating, so this is a little bit bumpy, but what it turns out is this is a parabola. Now that this estimation was probably a little off, maybe these are too, but it's roughly turns out to be a parabola. And we'll talk about why that's a parabola later. But for now, we're just practicing in our brains converting from a chart of positions to a chart of slopes. And that's what I want you to focus on for this homework. And